Hello everyone, welcome back to our CSCI 430, our operating system. And today we move on to a new topic, and today we'll introduce like what's the OS and including what are those are key functions. Okay, so we're going to summarize and describe those key functions and some design objective of an operating system. Okay, when we start to move on to like talk about OS, then we always ask a question. Okay, what is an OS? Okay, so referring, we talk about the managed sharing of resources, protection, isolation. Okay, here's some key functions we're going to do for an operating system. Okay, because we have so many different types of resources, including the memory, storage. Okay, we need to handle different tasks. Okay, so we need to think about how can we allocate those resources. Okay, and then if we have certain application, okay, use certain like use those like resources, how can we have like doing the isolation, like protect them, okay, and also like how about communication, know when will this task finish using those resources or to release it, okay. So all this referring, and then the illustrationist is they provide really clean and easy use the abstraction of physical resources. So to be honest, we talk about memory, like you're thinking we have like infinite like memory, or we do have a like dedicated machine, then we need to think about that. Okay. And also maybe we have some like high level objects, including files, user message, or this. Okay. So also like masking limitations and then virtualization, all this. So it's the operating system try to provide, okay, giving a really like kind of abstraction. Okay. And then also we kind of like using as a glue. Okay, what's a glue? So we do have some like common surface, okay, including handling storage, the Windows system. Okay, this Windows system you just more like general, not the like the Windows the system, but the Windows showing also the networking. Okay, you know, like for the internet coming in out. Okay, so all this will be the networking. And also, how can we talk about the like some permission like sharing authorization, okay, or like give it in kind of like combine them together. How do they look and feel? Okay, so this is related to OS, and also it giving a special layer like between the software and then try to provide so like application software access to hardware resources. Okay, so he is the middleman. Just thinking, okay, so it's a manager help us to manage all the resources, and then we have some let's say we have some guests. That means those like applications. Okay, if they need to use those resources, how can they use that? Okay, instead of directly talk to the hardware, we need a middleman. So it's the OS help us to do that. And then we try to provide some like convenient, like abstraction, like complex hardware devices. Okay. If we talk about hard drive I/O, okay, so we just say, okay, file. If you have some experience using the C++, okay, so if you need to get an input from the keyboard, so are you really need to reading each keystroke, like which key they input? No, you don't have, right? So you just need to like call the library have to handle it, and then the OS help you to waiting for the like what's the key input. Okay, so all this is IO, and also provide some like security and authentication. Okay, also giving us like some communication amongst like some logical entities. So that's like all the OS. Okay, we're going to provide you some features. And as an OS, okay, so it's a program. So even OS itself also is a program. It's like it's the first after you start your computer, okay, so from the BIOS, we load the your OS to the memory. Okay, it's actually your like one of program. So it controls all the execution of application program, okay, of them, and then also as an interface between the application and computer hardware. So it has three objectives. Okay, so you need to know what's the convenience. Okay, try to make the computer more convenient to use. Okay, as always, you can see the or maybe some like click on the button. Okay, look at the UI. Okay, so you click on it, easy to access. So you compare with the really like DOS computer. Okay, and you have to like input showing the list directory. Okay, also efficiency. So allow the system resources to be used efficiently because it helps us to manage all these resources. Let's say main memory loading from storage to main memory. Okay, and also I/O all these, okay, different devices, and also the ability to like evolve. So the OS should be also construct and allow effective development of a new system function. So is a the objective, like three key objective of OS. And so far, there's a pretty old chart is start by the Vista. So maybe you never heard about all this like version. So with the NASA stuff from it, like Windows 3.1, like NT, okay, Solus, and then 95, 98, okay, we just NT5 still, and then we have the Red Hat. Red Hat is one of the Linux, okay, and then we have the Windows XP is a most like really crazy, and I think it's that Windows like getting common. So, okay, so you see like going up, and then Vista. Okay, so you will see once the version like going to new, you see right here the source code right here. It really goes a million of lines. Okay, so you see it's getting more complex. If nowadays, let's say we have the um, maybe still some of you still stay on Windows 10, or you have to like upgrade to Windows 11. Suppose that you know like there's stopping support on Windows 10, so you have to upgrade to 11. So it's more like going higher. Okay, so how do we like tame the complexity? So every pieces of computer hardware, so they're different. They are different, like different CPU. Okay, nowadays, we talk about some ARM, okay, Pentium power PC. You maybe never heard about all this, okay, and because we have different manufacturer, okay, and also we have different amount of like memory, okay, the storage, like we do have like even manufacture different memory, different version like DDR3, 4, 5, okay, later coming like 6, and then this, okay, including like the hard drive, okay, or we have for SSD, and then we including different port like M2, so different type. Also we have the like the mouse, keyboard, sensor, like camera, okay, some like fingerprint with the, okay, touch screen, all this, and also like networking environment. We do have like cable. We don't have the DSL, but we do supporting the wireless. Okay, so all this. Okay, so you see so much like complex. Okay, and we have just a question I ask you. Just think about that. So does the programmer need to write a single program, perform like many independent activities? Do we really need to do that? Okay, and then the question, how about every program have to like alter for every piece of hardware? Should we do it in this way? And then if they're like there's a vector program like crash everything. Okay, so if we think about all this question, then we will comes out. It's like, how about just have a manager, give an OS, like help us to manage it, so we don't have to deal with all the like program hardware directly. Okay, so here's the idea we talk about it. And I'm giving you a graph right here. So you see how the operating system as a resource manager, okay, referee. So if we have the manager, we including maybe some like we do have a IO controller, okay. So those IO controller including like printer, keyboard, camera, whatever. Okay, of course on the memory we'll load as well. I say we'll load the OS. Okay, it will always occupy. So that's why every time when you turn on your computer, okay, so your memory already occupy certain like gigabyte. So everyone you can check. Um, Even you do not open any other application, you just should once you start your computer and then you check your like task manager, look at your memory. So it already like took you maybe 5 or 6 gigabytes. So of this. And then for the rest of memory, we do assign the program data or this, and then processor as the operating system. So we help us to manage all of these things. Okay. And here's a key point, like talking because we have different like hardware, okay, and we're not going to like touch all this hardware directly, okay, and that's why like the OS need to like help us to allocate. This way we talk about like allocate, okay, or certain resources we have to do in isolation. We are not allowed to touch it. Maybe like for the OS, we are not allowed to touch it. Okay, of course. In another level at cybersecurity, we'll talk about that, like how can we modify. But in this moment, no, you just need to know it, okay? And we try to provide some addressing and API. Because we need to implement or like develop certain program applications. How can we provide certain like some like for development? Okay, then maybe we can giving some useful abstraction like virtual machine. Okay, some like dedicated machine. Okay, also we can giving some infinite like memory for the VM. Also giving high level object like file, user message, reliable streaming, like transport message like TCP, IP, all this. So we can provide some APIs. Okay, we can call those API and then they perform certain action. But why not just knowing some general things? And when we talk about a process virtual machine, okay, so what's this? So those like programming simplicity, okay. So it's letting each process thinking it has all the memory or CPU type, okay. And each process, okay, think it owns all the devices. The benefits that you don't have to thinking, okay, how can I share with others, like taking turns? You don't have to care. So it's the process virtual machine, just thinking I have everything. And then different devices appear to have the same high level interface. Okay, because right here, it's possible that okay because for the interface sometimes we say the driver, okay, modules, okay, so they maybe have different weight, okay, so in different level. So but for the device they're the same high level, okay. And also the device interface is more powerful than the raw hardware, okay. Sometimes we do like one thing like big map display, okay, it's the Windows system or the Ethernet card, okay, so it can give a reliable order or like the networking TCP IP. So it can help us to handle it. So when we private the network card, okay. And also we have the fault isolation. If there's some process unable to directly like impact other process, so it's like called the one of isolation. Okay, so they're doing their own. Okay, reporting the isolation, and also if they do have some bugs, so it can crash the whole machine. Okay, if the OS itself has some bug, of course, if you know the boot screen, okay. But we later if you keep learning, they will know OS. So because we are kind of predicting next stage, okay. So we try to prevent it, but always there's some bugs. So that's why when you execute, let's say if you write a C++ program, execute if you wrote an infinite loop, okay, and then keep executing, taking all the resources. If you try to quit or kill the process, then it's fine. Okay, so it won't really crash the whole machine. Also protecting the protection and portability. So we just like giving an interface safe and stable across many platforms. So this is the idea like process virtual machine. So just looking, it's just a it owns all the memory or CPU time. And also it giving a key interface. Okay, so like OS as a this is like the kind of like we say is a for user or computer interface including instruction set, architecture, ISA, or the application binary interface, ABI, okay, and application programming interface. Okay, so this one is called API, okay, and also the GUI, okay, Windows system. So that's how we look at it and how can we feel it. So there's some like key interface we will dive into. If we look at it on the top, software including the application program always on the top, that means program we open, okay? And then the application programming interface help us like, to interact right here, so go down. Also we have some like binary interface, application binary right here. So we have the on the bottom, we have the operating system. Okay, help us to support all this. Okay, and then we have including the instruction set architecture. So if you see right here, it provides the interface ISA API. Okay, so it will be right here on the top, like software level. So you see, we never touch the hardware part. Okay, including the execution hardware, and maybe the bus, okay, interconnection like this, or like the memory translation, IO devices, or networking, or main memory. So the OS, like kind of like as a middleman, help us to provide interface between them. Okay, and also of course here's the interface for the like instruction. Okay, and then binary application binary, also the programming interface. So giving all this, okay, as a middle, so we don't have to really touch on the hardware. And just like help you to save time, you can look at the question. Okay, so it may like go back if you look at the question. So you may see, okay, what's not the principal function of a OS like this. So you can check it. So basically we can jump which one's not. We are helping not doing for the web. Okay, so should be C, right? So you can review all these questions and do it. If you have a question, and feel free to ask me. And then we move on about like, of course, when we talk about OS, so some like basic information about the OS stages and the history. Okay, and later I will try to add more fun, like manage the resources. But in this moment, you just learn, okay, about this. It's more likely just about some histories, okay, and talking about different stage. So like early stage OS, I think it's too old, not really helpful. So I just like quickly go through it and then start from early like batch system to modern complex multi-programming virtual memory, like based on this. But later we will also learn about what's the virtual memory, okay, paging, all this, okay. And really start from beginning, the stage including like serial processing, and then simple black batch system, and then later we start kind of like called supporting multi-program, okay, batch system, and then time sharing system like this. Really quick later about that. If you really old hardware, you know the OS, so like several discrete phases, and then at the time like hardware they come cheaper, and then they are humans, they're more expensive, they're paying for that, and we try to give them like PC workstation creation of like GUI. Okay, and that time because the hardware really cheap, so they can kind of like really expensive for the humans. So they were like ambiguous the devices, and also like well spreading the network, and this happened. And in the earliest like computer, we say the serial processing. Okay, we have no OS. So the program need to interact directly with the computer hardware. So if you know that was the serial connection, if some of you really touch um, some still there, maybe, so you really hard to imagine it because you need to like run from the console. Okay, so they have really display the lights like touch a switch or sometimes like certain input device and printer. Okay, so they need to access in the series. Okay, and only one thing right here, they cause two problems, is the scheduling and then setup time. So the most installation, so they use it on the like hard copy, sign up sheets, and then reserve the computer time and then time allocation. So can one night maybe somebody short or long. Okay, so maybe kind of like wasting the computer time. Also, and then when set up, it's like it kind of like considerable amount of time. So what they spend just on like setting up the program to run. Okay. Right now nowadays you can't like really hard even to us they say it's too hard to imagine it, even like for me because we're pretty close in our age. So even I never see those things. Okay. And then we have some like simple batch system. So in the early computer, okay, it's kind of like very expensive. Okay, so it's more important to maximize the processor like utilization. When we build a processor, also expensive, and also it can provide a monitor. Okay, so user no longer like, have direct access to processor. All these job they will submit to the computer operator, so like who like batch them together and paste them and then input device, so and then they read it, okay, and execute it. Those like program batches like back to the monitor when they finish, so they will appear and show up and display, right? That's how it looks like as a batch system. As a monitor point of view, when we see, so the monitor controls a sequence of events, and then we try to like interrupt, maybe something like interrupt processing, device drivers, like job sequencing, or some like control language interpreter. So all this bundle. And when we look at the memory right here for the West will be the user program area. So right here, it's still not like count as an OS, but like count before the OS right here. So, and then there's a like resonance monitor. So the software like OS in the memory, they over there, they try to read the job and giving control. Also return the control to the monitor of the compute and the job we're doing this way. And kind of like the concept before the OS, right? And from the processor point of view, when look at processor, they execute instruction from the memory containing the monitor because you have some idea like we try to loading from the memory, okay? And then when they execute instruction in the user program, okay, so until it can like end of it or some like error condition. So either we finish the whole program or error occur. So we saying that control is like passed to a job. That means that the process just like fetch it and execute the instruction. Okay, in the user program when we execute. And later controls they return to the monitor. That means that when the processor fetch and execute instruction from the monitor program. So it's like two way to doing this. And that's like what the processor like look at all these process. Okay, so like what kind of tasks they need to handle. So it's pretty straightforward and kind of like before OS. So maybe you are hard to imagine it. Okay, and also we have some desirable hardware features. Okay, let's say with the monitor or patch OS. So kind of like simply computer system. So we can rely on well-behaved job, like maybe including the memory protection, okay, give a timer, okay, or giving like privilege instruction, okay, including like compare the user or the kernel, okay, different type, or how can we handle interrupts. So all this, uh, this one, all this like closer to the hardware part, okay, and that's like for the monitor or the patch OS, like helping for it. And for the build, right now we're talking about the simple batch system, so kind of like overhead. So the processor time like alternate between execution, also the user program and the execution of monitor. We talk about these two parts, and then we have the square versions. There's like some maybe the memory is now like given over to the monitor. Okay, so once they really sacrifice it, okay, right? So some processor time also like consumed by the monitor too. So if they given to it, how can we have better management? Then we need to think about that. So that despite of the overhead, then a simple batch system improve the utilization of computer. So why not say, yeah, we already have the better one because nowadays we look at the OS, they actually fix this problem. So maybe you say it's really hard. So we like we need to roll back to really long time ago and then you think, okay, within that time, like for the hardware, we don't have OS. So we need to think about at that time the simple batch system already improved a lot. And just like telling you this utilization problem, okay, with like the simple batch system. So telling you if the processor is always like opens the idle, that means like processor always able to complete the task faster instead of like we reading like if we're reading from the file like or reading the files and then we execute it and then like we try to write one record to files. Okay, total. Okay, in total, but like the percentage of the CPU utilization only like using a 3.2%. That means that so far um it slow the processor because like others like read write IO devices. Okay, so it make the process just like most of the time. Okay, almost like 97% of time just waiting. And we need to think about like, okay, how can we improve it? And mainly reason because it's called the unit programming causing it. If we have a program, Let's say we have a program A. So we start to run, okay, after we run and then time's going and then we just like keep waiting and then run it again and keep on waiting. So the process most of the time spend a certain amount of time like executing it and until it reach an IO instruction and must then just wait until the IO instruction conclude before like process. So we just like kind of like waiting for input. Once it finish, then we keep on go back to running. So it's like called a unit programming, of course. Then we introduce the idea about like what's the multi-programming. Okay. For unit program examples, because we say we always running one program at that time, right? At that time, we call the MS like the DOS or early the MS-DOS or the batch processing. So it's kind of like early for the OS builder. So kind of like get rid of concurrency. Okay. So always only one thread, a thread accessing resources. But we will ask the question, like, does it really make sense? Like we kind of spending 97% of time, like just the CPU wait, idle and waiting for it. So that's why we introduced, how about we can make it like multi-programming? Can we run more than one program at a time? Okay, so that's why like we introduce more. Sometimes we call it like multitasking, but multitasking have another meaning. So multi-programming and multi-tasking try to not um confuse of them. Okay, and just thinking that means like later we will learn how can the OS helping for manage tasks. Okay, how can we manage process? Okay, so try to utilize the CPU. Okay, let it always executing but not waiting. Okay, so here's the idea. And for programming, as a following answer, so it's like kind of like multitasking. So maybe the memory we expand to hold like 3, 4, or like more programs, and then switch amount of them. So here's the idea of like multi-programming. That's what they're doing. For the batch or something like that, we always loading one program and run right and waiting for input like IO and then run it again. But for this one, we can keep on switching between different programs or applications. That's how it works. And you will see right here, maybe we have the application A, we will execute it and then waiting for input. Then we put in program B, just wait. Once we finish, then we will run program B and then waiting for it. And when we combine them together, you will see, okay, we will execute A, B, and then just wait. So you see the waiting time will be shortened right here. So, but here's the idea you will need to pay attention is we must be like have enough memory to hold the OS like beside a monitor, also like one user program. Okay. And also one job that need to wait for IO, then process can like switch to other job. So which is like no waiting. Okay. Okay, for the IO. So that means we keep running. So if we have enough memory space, that means we can add like program C, D, E, and then they keep waiting. Once A is ready, after getting input, okay, or IO, then we can switch back to program A. So you see right now there's no more waiting time. So it's the multi-programming. Um, Here is the utilization like histogram. Okay, you can showing maybe it's the processing time like if one 0 to 100% for CPU like execute for a certain time and then keep waiting right here. And for memory, no huge change. Okay, in the beginning because we loading the basic and then just say maybe loading one application goes a little bit and that's it. And for the disk, nothing to do. Maybe later after we execute for IO. Okay, so we have like fully to decide because we need to run it. Okay, to read or save the data, and then terminal for sometimes like because we need to reading file certain, so it's like terminal need to help and or like another IO printer. Okay, so past this time. So if you see like job 1, 2 waiting and the last job. Okay, this is the kind of like doing in the unit programming. But if we have the doing in the multiple programming, you see slightly extend a little bit, and then the CPU like it goes slightly higher, utilization is higher. Okay, because it depends on the task. Okay, And then the memory, you see, they're running utilize more because when we last longer, so we have different tasks and then terminal in the background and keep executing. And this we can execute earlier. And also the printer, so we put the execute earlier. So all these three jobs like can execute, okay, start in the same time, okay, and then depends on their task. Okay, maybe some of them finish earlier, some of them like last longer. So here's the differences between multi-programming. So it's like it's taking time. So also it can finish like around like at 15 right here, but for the unit programming, if it stop at 30. So you see the time difference. And we will ask a question because, of course, like multi-programming, okay, because here is the really key important concept about multi-programming. Also, here's a reason why we introduce OS, okay. But we do have a challenge. That means the OS need to solve this challenge. Otherwise, we cannot like really use OS, right? So here's the thing, because each application want to own the like machine, okay? So kind of like virtual machine abstraction, if you remember, process like virtual machine. They're thinking they are taking like all the process, right? And then the application, they compete with each other for resources. So we need to like have arbitrary access to share resources, like concurrency. And then also they need to protect the application from each other. Like this one is called the protection. So how can we protect like the application from each other's? Okay, try to maybe avoid any conflict. Also the access to the resources. Later I will give you some tasks because I know you have a first assignment. I will let you finish the first assignment. And then another task is how we design how to share resources. Later we will also talk about different mechanism. How can we manage well? Okay, but in this slide, still introduce some background. Also, some application need to communicate and cooperate with others like concurrency. So also like it's the extended of it. So here's the challenge. And then we move on like to about the time sharing system. So it's like kind of like used to handle multiple interact jobs. Okay, so the process time is shared among multiple users, and here's the idea. And then multiple users like simultaneously like access the system through the terminal with the OS interleaving the execution of each user program. So it's like short burst or like quantum of computation. So here's the idea of like time sharing. Kind of pretty similar right now. So we apply this one. So far, when we compare the batch multi-programming with the time sharing, we can see the principle of the objective is that we try to maximize the processor use. And for the time sharing, the purpose try to minimize the response time. Okay, because there's a different differences because in the beginning we discussed because most of the time is idle. So that's why we cannot tell. Okay. And then we have the source of the like directive to the operating system. So mainly for the batch, the job control language like command provide with the jobs. But for time sharing, it's the command enter at the terminal. So here's the differences between the source to the OS. So after we compare it, you can, if you're interested, you can look at the review, okay, and look at the question, and you can discuss it. Here's just let you think about there's a problem you think about it if there's an IO bound program. So one of that if you it runs along, okay, so we spend more time waiting for IO than using the processor. So if a processor bound program is the opposite. So suppose like a short scheduling algorithm like favor those like programs that have used a little processor time in the recent past, then maybe we need to explain, okay, with this algorithm favor the IO bound programs and yet does not like permanently deny processor time to process bound program. So we can think about this question like based on this. Okay. When we discuss it, we'll talk about more like coexistence of the IO. But so far, because we are like keep on thinking, but I will stop by our lecture in right here and come back later. We'll talk about more like major achievement in the OS design. Just to let you think about it, because nowadays I say if you want to apply this one, it's really fit on this design, because the Windows or the OS we are using right now, actually we already achieved like multi-count, like multitasking, multi-threading. Then later we talk about multi-threading. So we try to utilize the processor time. Also, they have a sharing time sharing feature. Okay, so everyone have a kind of like similar time to complete the task. To be fair, okay. And later we will learn about how do they work. Okay, but right here, if you're interested, you can look at the problem, and then we'll come back about the OS design. Thank you.